My name is Forrest Apollo. This is my GIS dissertation presentation, which is applying modern, publicly accessible GIS techniques for future sea level rise of the North Shore of Vancouver. This is an introduction to sea level rise in the study area itself. Numerous studies have predicted that over the next coming years, an increase of sea level rise will occur because of the global temperature increase due to climate change. The study area was the North Shore of Vancouver. The metro area of Vancouver is considered to be amongst the most vulnerable cities to SLR. The North Shore itself is surrounded by 3 bodies of water, and most of its economy relies on the coastal regions, especially shipping. There have been no major studies completed on the effects of sea level rise that are focused on the North Shore that I could find. These are the aims and objectives for this study. Um, the aim of this project is to create a more precise, publicly accessible interactive online map using modern GIS techniques that allow the public to explore the impacts of sea level rise due to climate change with its direct impact to key well-known places for residences of the North Shore using new high-resolution data and deep learning. To achieve these aims, there are 3 objectives. The first one is to demonstrate which areas will be inundated on the coast at 1 meter, 2 meter, 3 meter, 4 meter SLR by using 1 meter resolution LiDAR digital elevation model, implementing the bathtub method model with hydrologic connectivity. The second objective is to create a land use map of these areas and predict future changes in the land use with modern methods including deep learning. The third objective is to create an interactive online map detailing findings for the public to explore negative sea level rise impacts to the local infrastructure, commercial areas, and residential areas. This is my flowchart for the dissertation. There are 4 columns, and they're based off of my objectives. Column A is objective 3, column B is objective 1, and column C and D are objective 2, with column C being present LULC and column D being future LULC. All of the columns have data based off of B all layers, which are 1 meter SLR, 2 meter, 3 meter, and 4 meters. And the end products, besides column D, all end at the interactive online map. So these next few slides will discuss each objective's methodology, lit review, and results. The first objective is sea level rise, or SLR. This study uses a 1 meter resolution LiDAR DTM and bathtub method model with hydrologic connectivity to create 4 layers. SLR needs fine increments of data, preferably 1 meter or less in resolution. LiDAR DTM usually have better resolution data and higher vertical accuracy than satellite DTMs. Bathtub method is one of the most extensively used to delineate inundation zones. When used with hydrologic connectivity, inundation only occurs in areas that are directly connected to oceans. The results for sea level rise found that most of the inundation that occurs that is not beach areas is at 3 meters and 4 meters, with 3 meters inundating 2% of the total study area and 4 meters inundating 4.3% of the total area. Most of the flooding occurs in two areas as seen in the two inserts of the map to the right. This data is further discussed in the results section of my dissertation. This slide is a comparison between the study's SLR map and readily available SLR web map. That is called Coastal DEMs created by Climate Central. The main difference between these two maps is that mine is 1 meters in resolution, whereas theirs is 30 meters plus for resolution for the area of the North Shore. The main difference between the two examples seen above is that Coastal DEMs predicts that the whole of the southern and eastern parts of this example will be flooded, whereas mine predicts that most of the area will be flooded besides the buildings and the raised railroad line. Land use land cover, or LULC, is an important part of sea level rise based studies because it demonstrates what types of areas will be affected by inundation. These maps can be created from aerial or satellite images that are classified into different categories by classifying different pixels. For this study, a 2021 Sentinel-2 10-meter land use land cover time series from Esri was used and was then clipped with each sea level rise layer that was created in the last slide. This was used after a failed attempt to create my own LULC with deep learning CNN. For this LULC, 82.81% of the area that would be inundated would be built areas if 4-meter inundation occurs. Built areas was the highest class throughout the sea level rise layers besides 1-meter SLR. This is further discussed in my results. Since there will be changes for the current LULC of the study area when the 1 meter to 4 meter sea level rise might occur, the study uses past land cover changes to predict future ones in Terraset's land change modeler. This was particularly important because of the long-term time range to achieve 1 meter to 4 meter rise in sea level, if at all. In Terraset, LULC maps were created from Landsat 5 images from the years 1991, 2006, and 2011. The land change modeler used the 1991 and 2006 land cover maps as well as other maps that I created, such as distance from roads, to loosely predict the future land use. The 2011 LULC was used to validate results. The future predicted LULC years that were chosen were 2100, 2200, and 2300. These dates were chosen since studies predict for this region that 1 meter SLR will occur in 2100, 2 meter in 2200, and 4 meter in 2300. Multi-layer perceptrons and Markov's chain transition were used to create a transition prediction model which had an accuracy of 67.6%. The results of the land change cover that would be inundated was quite similar to the current LULC, other than there was an increased percent of the class built areas that would be flooded. This is the last objective: public interactive map and video. Studies recommend demonstrating inundation of the local areas to the public reduces the abstractness of the effects of climate change. This is especially the case for key locations, and in this study, these areas will be highlighted with pop-ups. There were 9 locations that were chosen that are important economic, industrial, and environmental areas. These pop-ups had a photograph, link to a website, and a description text of what it means to the community. The layers that were also used were the 4 SLR layers and the 2021 LUC of the full study area. Besides the interactive map, a 3D flyover was created showing the flooded area with 3D buildings that would be inundated. A story map was made that included these two. I will demonstrate it at the end of these slides. The dissertation fulfills its aims and objectives. Through the results from the study, a more precise, publicly accessible, interactive online map that allows the public to explore the impacts of sea level rise due to climate change with its direct impacts to key well-known places for the residents of the North Shore of Vancouver was successfully created. The creation of an online interactive map, Objective 1, that has layers that include SLR 1 meter to 4 meters, Objective 1, current land use, land cover, and future land use, land cover, Objective 2. This fulfills the objectives demonstrating which areas will be inundated, creating a land use map of these areas, and predicting future land changes in land use, and creating an interactive online map detailing findings so the public can explore negative SLR impacts to the local major infrastructures, commercial and residential areas. There were 5 major limitations in the study. One of them was the precision of both the current and future LULCs. This is in part due to predicting LULCs over hundreds of years from the current date, the unpredictability of growth of the study area, and how the current and future LULCs cannot be compared one-to-one due to different satellites, classifications, and resolutions. The other limitations are discussed in my dissertation as well as future works. This is my study map. This is the video I created with each layer of SLR included and buildings that were extruded from the DSM. And the DTM was used as the overall height. This is a little blurb. And this is my interactive map. This is the whole study area. And as you can see, each of the layers was transparent, so you can see the satellite image below, so that locals could see their houses or other locations. This is the legend. And this is the pop-up with a little blurb and a link to their webpage. This just shows the extent, with each color being a different layer. And this is another pop-up. This is the other video with the heights of the buildings and sea level layers being amplified and the colors being the same as the interactive map. A step-by-step guideline is made in Appendix A for other municipalities to make their own. Thanks.